Thank you so much. So I am Edwiga Renald. I am from the School of Computational and Communication Science and Engineering from the Nelson Mandela African Institution of Science and Technology. And I would like to kindly give my thanks to the organizers of this esteemed symposium for inviting me and granting me chance to present part of my work in this day. So I would like to present this part of my thesis titled Control of Lumpy Skin Disease of Cattle, Coupling Mathematical Modeling with Deep Learning. So I will take you through this presentation outline, which covers the introduction, then the deterministic model development. Later on, we went on with the analysis of uncertainty due to data availability, then integration of the deep learning into the deterministic model, then extension to the stochastic model, and conclusion, and lastly, references. And the conclusion is made on this presentation. So to start with, lumpy skin disease of cattle is a viral disease of cattle caused by lumpy skin disease virus, which is a member of Capripox virus genus in the Poxviridae family. So one of the symptoms include fever, nodules on the skin, over discharge of saliva, and also lacrimation. So mortality of this disease ranges from 1% to 3%, but depending on the susceptibility of a host, it can be as high as 20% to 85%. And once it entered into a herd or a farm, it can lead to a loss of about $1,176 US. So it is transmitted mechanically through blood-feeding insect species, such as ticks, flies, and mosquitoes. And what happens is that when a healthy vector go and bite an infected cattle in the process of feeding, and then it go on and bite a healthy cattle, that's how it transmits the virus. So figure 2 represents the clinical representation of the disease. This is the actual view, and this is a microscopic view under the skin. So these problems seriously need attention regarding to coming up with intervention strategies because of the economic loss. It can lead to death, milk reduction, poor quality of animal products, and also it can lead to sterility in bulls and also infertility to cows. Moreover, the World Organization of Animal Health regards this as a notifiable transboundary disease. And in our country, in the United Republic of Tanzania, through our Ministry of Livestock and Fisheries, regarded this as one of the 13 strategic livestock diseases to deal with in one of the financial years in the year 2020-2021. So the current intervention strategy is vaccination, but it has its challenges, such as the costs of the vaccines and the vaccination process. So when the vaccines are produced, they need to be kept in a very cold temperature, and also when transporting them for the purpose of utilization, then they need to be stored in refrigeration temperature. So a few farmers can afford these costs, and in most cases are those business farmers are the ones who dare to incur the costs. In most cases, farmers are not able, so the losses happen. Also, the vaccines vary in terms of their efficacy and also their side effects. And the effective vaccines, their protective ability lasts for 1 year. So it means someone should conduct vaccination process yearly, which is costful. Now, we thought of a mathematical modeling approach whereby we wanted to use this tool to come up with other intervention strategies that may supplement this current strategy. So under assumption that this disease is transmitted by mechanical vectors, and that there is the incubation period for vectors is not yet known. So we developed a compartmental model which involve interaction of two populations, the cattle population and also the vectors population, whereby these two populations interact and they cause transmission of the virus. So we have a deterministic, susceptible, exposed, infectious, recovered, then susceptible model. In this model, we are having several parameters which explain progression of different individuals from various classes depending on disease state to subsequent classes. So from the model compartment, we are having this set of differential equations, and here is the definition of infection rate for the two populations, whereby we can see that we are defining the infection rates as they depend on parameter A, which is a biting rate, and also the probabilities of infection from either population to another one, and also the proportion of infectious individuals in a corresponding population. So in here, for instance, with the infection rate lambda C, here when these infectious vectors interact with susceptible cattle is where the infection occur. And also on the other hand, for the lambda V, the infection rate for the vectors, when the infectious vector interact with these susceptible vectors, then transmission of virus occur from the infectious cattle to the susceptible vectors. So we also defined these as our initial conditions for the model. Some basic theoretical analysis of the model were done, such as determining the invariant region and also testing for the positivity of the solution. And also we were able to determine the disease-free equilibrium point and tested it for its theoretical stability, both locally and globally, and found that it is stable, because theoretically, and also we tested it numerically as well. We were also able to determine the endemic equilibrium points, and we tested it for stability, and we found that it is both theoretically and numerically stable. Also, we made use of the next generation matrix, and so we calculated this basic reproduction number threshold, so as it may guide us towards the extinction and persistence of this disease. Now, before utilizing the model, we wanted to test for its reliability in using. So as we know, when you are having a model, the next thing is to estimate model parameters and do the simulations. Now, here we generated synthetic data by adding a Gaussian noise to our model solution using parameter sets from the literature, and came up with an observed data resembling real data. So here we added a Gaussian noise of size 0.0801. And we performed the least square fitting by fitting the model to the data using these initial conditions. And we found that there is a very good match between the data and our model, and that we can conclude that the model is good for use. Also, we didn't rely on the synthetic data alone. We tried to fit our model to 150 LSD cases from water farm in Ethiopia, and find that also the model has a good match between it and the data. And so we concluded that this model is reliable and usable in various settings. Now, since we are relying on the general case of the model, we used parameter estimates from the synthetic data fitting to conduct a global sensitivity analysis to assess how our model parameters and our variables relate in a nonlinear monotonic manner. So here we used Latin hypercube sampling technique to sample parameter values from an evenly probable distribution, and use the parameters to calculate the partial rank correlation coefficients. And we find that the recruitment rate, now this is for the cattle population, and here, since our interest is to eliminate LSD in both cattle population and vectors population, we wanted to to bring down the size of infectious cases in both populations. So our parameters of interest are the infectious individuals in cattle and vectors population. So with cattle population, we saw that the lambda C, the recruitment rate of cattle, was having a most positive sensitivity index, followed by the biting rate. And next is the probability of infection from infectious vector to susceptible cattle, and also the probability of infection from infectious cattle to susceptible vector. On the other hand, we saw that the recovery rate is having a most negative sensitive index, followed by the natural death rate of cattle. So what does this tell us? This tells us that we need to apply measures to reduce the biting rate and also to reduce the probabilities of infection from either population to another. Moreover, here, mathematically, we can interpret that we need to reduce recruitment, but this cannot be a desired control because we want to keep on doing the livestock keeping. So we cannot advise that we need to reduce recruitment. On the other hand, we need to apply measures to facilitate recovery of individuals, and also here we can also see that the mortality rate is having negative. So instead of letting these people, these individuals die, then we can instead do some quarantine and isolation. We isolate them from the population and ensure proper nutritional management and healthy keeping practices so that we fasten their recovery instead of letting them die. So when should we apply these measures? This figure B tells us we can see that these sensitive parameters are having their values at the first days of the infection period. So we are suggesting these measures to be given priority at the beginning. Moreover, on the vectors population is just more or less in the analysis of the cattle population, but here we can see that the recruitment rate is having a very high value of sensitivity index, suggesting that we need to control recruitment of vectors in cattle farms. Now, how can we do that? We can apply insecticides for those vectors who are in eggs and larva stage, so that we can control the recruitment of the adults, the population of adults who are the ones who able to bite and transmit the virus. Also, we can see that here it is gaining significance, the same parameter, around the 10th day, where vectors are already matured and they can cause transmission. So this approach should be applied in the first days of the outbreak as well. So having determined sensitive parameters, we wanted to plot a contour plot which investigate a combined effect of two parameters or doubled parameters on the reproduction number. So here we can see that when the biting rate is reduced and the probability of infection from infectious cattle is reduced, the basic reproduction number become small. And also here we can see that when basic reproduction number is reduced and the recovery rate is increased, then the basic reproduction number becomes very low. So we are suggesting combined efforts of measures that target control of vector bites and increasing in recovery so as to be able to eradicate LSD in both cattle and vectors population. Moreover, after having satisfied with the reliability of our model, we wanted to test now the uncertainty due to that data availability by specifically assessing some specific features of data, whereby we involved 3 features: the level of the noise, length of time for the available data, number of model classes for which the data is available, by leveraging the adaptive MCMC by Professor Heikki Harjo, and ran 12,000 simulations. So in here, we are having our parameter values, some of our parameter values, which we treat them as true values. And then we run MCMC results in 3 cases for each case, whereby, for instance, here we are comparing MCMC results when we are having data for the infectious cattle class alone, when you are having also for data for the susceptible cattle and infectious, and when we are having data for all 4 compartments. Now with the green results is MCMC results when we are having the data for the 4 classes. Now the red one is when you are having data for the 2 classes, and the blue ones is when you are having data for the 1 class only. We can see that when you are having 4 classes, the MCMC results are confining themselves with the true value, indicating that we are having much less uncertainty compared to when you are having very few class data available. When we compare the case of length of time, we can see that the more the time we are having, the more the MCMC results confine themselves with the true value, and which indicate the less the uncertainty. Also, for the case of level of noise in the available data, we can see that the less the noise we are having, the less the uncertainty, the green results, and the more the noise, which is indicated, for instance, in the blue results, or the more the noise increase, like from these MCMC results for the green, then when you increase noise, then it results to these red results, and when you keep on increasing the noise, the blue results now. You see that the more we increase the noise, the more the sampled parameter values run away from the true value, indicating that that is the increase in the uncertainty. So after realizing that now we need enough data in terms of time points and model classes with less amount of noise, then we wanted to find a framework whereby it can accommodate the challenge of the few data, because we have challenge with data availability, and also a framework which is more of learning data trajectory other than fitting. Now, deep learning has been a predominant method which is very powerful in learning data. So in here, we integrated our deterministic model with deep learning and come up with a physics-informed neural network scheme for the LSD SEIRS model. So how does this work? Initially, we find the deep learning solution normally as it is done. So here, in between here, there is an update of the weights and biases, and with the help of the activation function hyperbolic tangent, we have the deep learning solution. So we take the deep learning solution and enforce it through the identity operator and the residual function. We will see it in the next slide, to come up with an error, which is a loss. I have called it EC, that at the end of the day will need to be minimized numerically, and the results will be now parameter values that leads to the most minimum loss. What is the loss function? Here it is. We have the data error, whereby for each deep learning solution, we calculate the difference between the deep learning solution and the data, and we square it, and we find, of course, the mean. And also for each deep learning solution, a corresponding derivative is computed through the process known as automatic differentiation. And also the solution is taken and substituted to the right-hand side equation of the infectious cattle class. And so all these two are summed and come up with a loss function, whereby it is numerically minimized with the help of Levenberg-Marquardt algorithm. So at the end of the day, we will want a parameter set theta, which results to the most minimum loss for this function. Upon doing that, we came up with these parameter values, and these initial values are just obtained from literature, from experimental studies. So we wanted to view the accuracy of our PINNS by viewing the correlation results. So these were done in MATLAB R 2021. So in the training, MATLAB automatically split the data into 70% for training, 15% for validation, and 15% for testing, and the 100% data by finding the Pearson correlation coefficient between the data, the input, and the output. So results here indicate that there is a very big correlation between our input and our output for all cases, indicating that the framework has performed well in the prediction. So after having the parameters at hand, we wanted now to do numerical simulations. But again, we were not interested in focusing on simulating numerically the deterministic model, because it misses the inherent variability that is present in real systems. So the deterministic model doesn't capture that. Now instead, we extended the model to a stochastic model in order to accommodate that. And we did that by parametric perturbation of our deterministic model by adding a white noise in our biting rate parameter. So this is the noise intensity, and this is the standard Brownian motion, which varies with time. So from there, we are having this set of stochastic differential equations. And then we used now the obtained parameters from the PINS framework to simulate the incidence of LSD using the stochastic model. So in here, we can see that the susceptible individuals are decreased in the first 30 days, and the exposed individuals are increasing between day 4 and around day 28, which corroborates with the fact that the incubation period for this disease in cattle population lies between day 4 and day 28. Moreover, we can see that the recovery in the recovered class reaches its maximum around day 60 or 60 something. This resembles also other findings that the recovery for this disease takes a few months, between 2 months to 6 months. In this case, we also see that in the vectors population, so here there are 2 classes. So it means when these susceptible individuals contract the virus, the number of healthy individuals in this population decline, resulting to an increase in the infectious population. So we wanted also to, having identified biting rate as one of the sensitive parameters, we wanted to vary it and assess it, the population impact of varying this parameter using the stochastic model. So we can see that in both exposed cattle and infectious vectors, when this parameter increases, we can see that these groups of individuals increases as well, while taking into account the randomness that is present in the stochastic model. Also for the infectious cattle, the more the biting rate increases, this infectious cattle group also increases. Why were we interested in assessing this? We wanted to test the parameter values that came from the physics-informed neural networks, if they could portray the same results as what we saw in the deterministic model. So this is to cement the accuracy of our framework. So as a conclusion, in this work, LSD mathematical models have been developed and analyzed. Parameters can be accurately identified from data with reasonable level of noise and sufficient data points spanning through model classes. And also model analysis results have pointed out possible intervention strategies, which is vector control to supplement vaccination, and also the quarantine in the isolation. And here, measures targeting minimization now of vector biting rate are crucial. Now for the policy briefing, we kindly recommend data collection to be methodical, meaning systematic, to ensure that enough information is gathered, and also data processing should be efficient. In the vector control strategy, for the adults, we are suggesting application of repellents instead of insecticides, because most vectors now are becoming very competent against insecticides. So instead, we are suggesting application of repellents in cattle farms and herds. And also we are suggesting biological control methods, such as the establishment of copypods, livelihoods around livestock farms or herds. These copypods will be predating vectors. So the vectors will be the prey and this will be predators. So from the work, we were able to publish this manuscript whereby on top of just the simulation using the stochastic model, we also established the conditions for extinction and persistence using the stochastic model, and they were tested numerically using the estimated parameters, and they aligned with what the theoretical solutions said. So we also had other relevant publications from the work and the product. Here we have 3 more publications, and also we came up with an LSD app, which is a MATLAB-based desktop application, a graphical user interface for data input, parameter estimation, and visualizing of LSD incidences using the physics-informed neural network, and also the stochastic model simulation, and also viewing the conditions for extinction and persistence. So these are some of my references that I used in the work. I would like to acknowledge the following. I thank my university, Nelson Mandela African Institution of Science and Technology, for granting admission to pursue my PhD studies. And also I would like to thank our Ministry of Education, Science and Technology for providing sponsorship, partial sponsorship under the Higher Education for Economic Transformation project. And also I thank the International Mathematical Union for they granted me some partial support at the beginning before receiving this scholarship. They granted me some partial sponsorship, partial support, which enabled me to register my PhD studies. I would like also to thank my colleagues, friends, and family, and all other people mentioned and unmentioned, but specifically and in a special way, I would kindly like to thank my supervisors, Professor Dr. Engineer Verdiana Grace Masanja, because 75% of the work, I got the ideas from her. So my work was to implement what she was instructing. And so she supervised me in a very good collaboration and cooperation with Professor Joram Buza from the School of Life Sciences and Biomedical Engineering, and also Professor Jean-Michel Chuenche, who is our adjunct professor in the School of Computational and Communication Sciences and Engineering. Thank you so much.